In this video, we're gonna talk about alternating series. Okay, so alternating series will be the series that in the form of summation n equal to 1 to infinity of -1 to the n or -1 to the n minus 1, and the important term turn out to be bn, which is always positive. So it's gonna turn out to be going up, down, up, down, up, down, up, down like this. So the term -1 gonna make your sequence turn out to be like going up, going down, going up, going down. So that's why we call this thing alternate. Okay, so it's gonna alternate up, down, up, down, up, down. So, and the series that happen in this way is gonna be alternating series. Okay, for example, it's gonna be 0, -1, series, it's gonna be n, sorry. So for this one, it's gonna be n equal to 1 to infinity of -1 to the n over n. So it's gonna be 1, it's gonna have to be -n, so it's not correct. So it's gonna be -1 here also, okay? So the thing that you see here is gonna be, you have series n equal to 1 to infinity of -1 to the n minus 1 over n. So this will give you when n equal to 1 is going to be 1. When n equal to 2 is going to be -1 over 2 plus 1/3, and you continue. So you see that you're going to have the sign positive, negative, positive, negative alternately. Okay, and the alternate series will have a test that called alternating series test in order to test whether this series convergent. When you like to use alternating series test, it's gonna give you only one answer. It's gonna be conversion. Okay, and the way that we're gonna test this thing is gonna be, we're gonna see only the sequence bn. So it's going to be just, you can just ignore -1 to the n minus 1 or -1 to the n, and you're going to work only on the sequence bn that you have. So the thing that you need to check is going to be, you need to check with the limit n go to infinity of bn is equal to 0, and you're gonna have to check also that the sequence bn is decreasing. For checking decreasing, you can check this guy in two ways. So it's gonna be just, you can just use direct comparison. So it's gonna be n plus 1 more than n, and you continue working on this one. Or another one, you can just differentiate f prime smaller than or equal to 0. Okay, so you have to, in order to test whether your sequence is is decreasing. And the conclusion for this guy turned out to be conversion. If you want to show that alternate series turned out to be divergent, it's gonna be, you gonna have to check whether limit n go to infinity of bn turn out to be not equal to 0. Let me also make a remark here. Okay, so if limit n go to infinity of bn does not equal to 0, okay, or does not exist, okay, then we know that the limit n go to infinity of -1 to the n bn turn out to be does not exist. Okay, so if you have that your limit n go to infinity of bn not equal to 0, or actually it should be better if you just say limit not equal to 0. It's gonna already include that not exist. So we're gonna just be able to conclude that limit n go to infinity of -1 to the n bn turn out to be does not exist. So we can conclude that the series n equal to 1 to infinity of -1 to the n bn turn out to be divergent by test for divergence. Okay, so that will be an important remark also. Okay, so if you show that the limit n go to infinity of bn does not equal to 0, we know that the limit n go to infinity of -1 to the n bn turn out to be does not exist, and the series will turn out to be divergent by test for divergence. It's not by AST, okay, so it's going to be not by the alternating series test. So this one I'm going to have an abbreviation for this one, AST. Okay, so let's try to do the example 23. So you like to test with a series n -1 to the n over n convergent or divergent. So you consider the first one first. So you have bn equal to 1 over n. So this is your sequence bn. And you have to check two things. It's going to be limit n go to infinity of 1 over n. This guy easily equal to 0. And the second one, you know that you have n plus 1 more than n. So you flip this one. It's going to be less than n, less than 1 over n. So you have bn plus 1 smaller than bn. Okay, so this one means that your 1 over n is decreasing. Okay, so the series n equal to 1 to infinity of -1 to the n over n is convergent by alternating series test. Okay, so that is going to be this test in order to conclude that your series turned out to be convergent. The next one, you see here that you're gonna have different bn. So for bn in the second case, you have n factorial. So it's gonna be bn equal to 1 over n factorial. And this guy, okay, turn out to be the sequence that you like to test. So you're gonna just find limit n go to infinity of 1 over n factorial, and this one is again is 1 over infinity, so it's gonna become 0. Okay, infinity factorial turn out to be really large, and the second one is gonna be n plus 1 more than n, so you have n plus 1 factorial is greater than n factorial, and you flip this one, so you have n plus 1 factorial smaller than 1 over n factorial. Okay, so you have the sequence 1 over n factorial is decreasing. Okay, and the conclusion turned out to be your series will be convergent by alternating series test. Okay, so this one is the thing that called alternating series test. The next one, you see that you have -1 to the n plus 1, which we're gonna ignore first, and then we're gonna identify bn. And in this case, your bn turned out to be square root. Okay, so you have bn equal to square root n over square root 2n minus 1. And this guy will be square root n over 2n minus 1. Okay, and you're gonna find limit n go to infinity of this bn. Okay, so this is your number one. So you have limit n go to infinity of square root n over 2n minus 1. Okay, so it's gonna be limit n go to infinity, and you see that it's gonna be n, and you have n 2 minus 1 over n, which can be cancelled like this one, and you have limit n go to infinity, this guy approaching 0. So this one will be 1 over root 2, and it's turned out not equal to 0. So when you have the limit not equal to 0, like I remarked earlier, okay, it's gonna turn out to be divergent. Okay, so your series turned out to be divergent by the test for divergence. So series n equal to 1 to infinity of -1 to the n plus 1 square root n over square root 2n minus 1 is divergent by the test for divergence. Okay, so that we don't need number 2 because we have limit not equal to 0. You cannot proceed to number 2. Similarly, for this one, I just let you do this one on your own. Try to find limit n go to infinity of 1 plus e to the n for me. And you're gonna see that it's gonna turn out to be not equal to 0, and you're gonna be able to conclude that the series turned out to be divergent. Okay, so this one is the green guy. Okay, and you have the limit of the green function turn out to be not equal to 0. I let you do this one first. The next one is this series. So you have series n equal to 1 to infinity of -1 to the n of log n over root n. So for this one, you have the green guy. Okay, so you have bn given by log n over root n. So you're gonna check limit n go to infinity of log n over root n. So for this one, you differentiate. So log n is gonna turn out to be, you dip on top, it's gonna be 1 over n. You dip on the bottom, so you get 1 over 2 root n. Okay, so this one by using the L'Hopital, you dip top and dip bottom. And you see that this one will be limit n go to infinity of 2 root n over n. So it's going to be 2 over root n. And you're going to have this one go to 0. Okay, so that is going to be number 1. Okay, so you have the limit equal to 0. For the second, that you need to show decreasing. For showing decreasing, you need to differentiate. So this one is kind of difficult to use direct comparison. Okay, so we not be able to like use direct comparison. So we're gonna let fx equal to log x over x inside square root. Okay, and you have x more than or equal to 1. Okay, and actually we're gonna differentiate f prime x to see whether it's decreasing or increasing. So you have square root, so the bottom derivative of the top minus the top derivative of the bottom. So it's going to be 1 over 2 root x over the bottom square. So you would get 1 over root x minus log x over 2 root x over x. Okay, so for this one, it's gonna be 2 minus log x over, okay, 2 minus log x over x root x. No, it's gonna be 2, right? So it's gonna be 2. And you see that for this guy, it's gonna be positive. This is because you have x positive, okay? And you have 2 minus log x. For 2 minus log x, this guy will turn out to be sometime positive. So it's going to be positive for y, like for x. So this one is going to be positive or negative. However, so when x, what should I say? When x more than e square, okay, so when x more than e square, log x will be more than log of e square, and this guy is equal to 2, okay? And what is e square? E square is 2.7, okay? And 2.7 square is about, I would say about 8 something, okay? So it's going to be about 8. So in this case, so when x more than 8, this guy will be more than 2, okay? So we're gonna conclude here that this guy is negative when x greater than or equal to 9, okay? So when x greater than or equal to 9, what does this one mean? It means that for x more than 9, this guy is gonna turn out to be negative. So we have this one. This one is a little bit confusing for some of you. Okay, I'm gonna explain this one slowly. So for this one, you see that we have to 8, to 9, to 10, and so on. So the meaning for this one is mean that we don't care about the value of the sequence up until the 8. Okay, so it can be anything, okay, up until here. And after 9, okay, after 9, I would suggest that it's going to be increasing like this. How many point? 1, 2, 3, 4, 5, 6, 7, 8. So we need 8 point. It may look like something like this, okay? And after 8, it's gonna turn out to be going down, okay? So after 8, it's turn out to be going down like this, okay? So you see that your sequence behave in the way that the first 8 term is increasing and the rest of the term after 8 turn out to be decreasing. This one is good enough to say the sequence is decreasing. Okay, so in this case, we're going to conclude that log n over root n is decreasing when n more than 9. Okay, so for this one, it's a little bit tricky, a little bit that you have to know some value of n that your sequence will begin going down. Okay, your sequence will be going down after some value. Okay, and it's gonna come from like a small solving equation. Like if you let this guy equal to 0, you must have x equal to e square, and you just estimate e square kind of. Okay, so for this one, it means that your sequence will behave in this way, and it's gonna be able to use the alternating series test in order to test that this series turn out to be convergent. Okay, we don't care about the first 8 term. Okay, so here we don't care about this first 8 term. The thing that we would care, so we don't care. Okay, the thing that we would care is going to turn out to be from the 8th term forward. So you see that this one, why did it turn out to be we care only for 9? So it means that you see here that it's going to be, let me have an. So if I call this term an, okay, if I call this term an, it means that this series turned out to be a1 plus a2 plus until you have a8. Okay, so let's just use a7, a7, a8, and you see that you just write n equal to 9 to infinity of an. And you see that the thing that you care is going to be that this guy conversion. Okay, so this guy conversion. This one is going to be just finite term. You just add 8 term to that conversion. So you'll be able to conclude that the whole thing will turn out to be conversion. So when we are testing for conversion, we can ignore like the first finite term, first 9 term, first 3 term. So we don't have to care on that. And we just like care only for the one that we have the sequence begin decreasing. Okay, so this is what you have. Okay, so this one will be just use alternating series. So we're gonna conclude that Okay, so we gonna conclude that the series n equal to 1 to infinity of negative 1 to the n log n over root n is convergent by alternating series test. Okay. The last one, I will let you do this one on your own. The thing is sometimes cos n pi, okay, sine n plus 1/2 pi, they are just another way to write negative 1 to the n. So when you see cos n pi, okay, so don't be afraid that it's going to be trigonometric series or something. So it's not going to be trigonometric series. For this one, you see that this guy transform into series n equal to 1 to infinity of n negative 1 to the n over e to the n. Okay, so you see that this guy transform into this, and you have your bn given by n over e to the n. Okay, so please try to use AST to test whether this series is convergent. Okay, so that is going to be, I'm gonna left you with this one. After knowing alternating series, we're gonna also be able to test any other series. Any other series, what does it mean for any other series? It means that when you do integral tests, when you do comparison tests, and when you do limit comparison tests, one requirement for that is you have non-negative term. Okay, so it's going to be the requirement that you have non-negative term in order to use this test. For alternating series, the series must be alternate, up, down, up, down, up, down. So the requirement turn out to be negative 1 to the n or negative 1 to the n minus 1 bn, and you're going to have bn always positive. So for any other series like this one, so you see that you not be able to control sine n. So when you see sine n, it's not cos n pi like before. So this one is sine n. So this guy can be positive, negative, and also not alternate. Okay. So for this one, it can be positive, it can be negative, and this guy not alternate. So for this series, okay, so for this series, the way to use alternating series is not possible because it's not alternate. This one is impossible to use comparison, limit comparison, or integral test because the term turned out to be not positive. So the thing that we can do is going to be, we can make this term to be always positive. In order to make this guy to be always positive, we're going to consider absolute value of an. Okay, so that the reason behind doing this one. So we're going to consider the series n equal to 1 to infinity of sine n over n, and you're going to put absolute value like this. Okay, so the difference is going to turn out to be you put absolute or not. Okay, it's going to be square. Okay, so the theorem say that a series is called absolutely convergent. Okay, so this is another vocabulary. So absolutely convergent means that your series with absolute value, okay, so you put absolute to each term, is turned out to be convergent. Okay, so absolutely convergent is mean the series of absolute value of an is a convergent series. Okay, and we have an important theorem that if you have the series turn out to be absolutely convergent, the series itself also convergent. Okay, so this is the result that we shall apply to this example. Okay, so the theorem here say that if you have the series of absolute of an turn out to be convergent, you allow to conclude that the series an itself also convergent. Okay, so that will be an important result for series. So if you be able to show that this series is convergent, okay, if you be able to show that this series is convergent, you can conclude that this series is also convergent. Let's try. So how would we use this one? Okay, so note that we be able to conclude that psi n over n square. Okay, so you have psi n over n square. Now is positive. Okay, so now it's greater than or equal to 0. So we know that this guy is positive. So we can use comparison test and absolute value of psi n less than or equal to 1. Okay, and you divide by n square both sides. Okay, so you divide by n square both sides. So you see that this one is less than this one and this one is bn. This one is absolute an. Okay, so you have absolute an less than or equal to bn, and we know that the series 1 over n square is a p equal to 2 greater than 1. So this guy is conversion. Okay, so we know that the series 1 over n square is convergent. So we be able to conclude that, okay, the series n equal to 1 to infinity of absolute psi n over n square is convergent by the comparison test. Okay, so it's turned out to be conversion by the comparison test. So from the above theorem, we can conclude that okay, so from the above theorem, we can conclude that the series n equal to 1 to infinity of psi n over n square is also conversion. Okay, so that's how we do this one. Okay, so if you have the series that you not be able to control, just put absolute value. If you have the series turn out to be conversion with absolute value, the series itself turn out to be also conversion. However, we have shown in this script that the series n equal to 1 to infinity of negative 1 to the n over n is conversion. Okay, so we have shown in example, I would say it's example 23, number 1. Okay, so for this guy, it is example 23, number 1. Okay, is conversion. And when you put absolute value, okay, when you put absolute value, it turns out to be harmonic series. And we also have shown that this series is divergent. So you see that it's not true to say, okay, so this one is not true to say, so I will circle not true. So it's not true to say that if you have the series is convergent, okay, so if the series is convergent, the series of absolute value turn out to be also convergent. Okay, so if your series itself is convergent, you cannot say anything about the series of absolute value. It can be convergent or it can be divergent. Okay, so it's gonna turn out to be the thing. Okay. Okay. The next one is a series. Okay, so a series is called conditionally conversion. This one I have a typo here. It's gonna be conditionally. Okay, so it's null. So this one turned out to be nully. Okay, so this one is called conditionally conversion. Okay, if it is conversion but its absolute value turn out to be divergent. Okay, so it's conversion, but it's not absolute conversion. For example, you have the series -1 to the n. Itself is conversion. When you put absolute value, turn out to be divergent. So this series of this kind turn out to be called conditionally conversion. Okay, so we're gonna show that this series is conditionally conversion. When you like to show that the series is conditionally conversion, the thing that you need to show is going to be, okay, so you must show the series itself is conversion. Okay, so you must show that the series itself is conversion, and you show series n equal to 1 to infinity of absolute value. Okay, so it's gonna be absolute value of -1 to the n log n over n is divergent. Okay, so you show that the series is convergent and absolute value turn out to be divergent. Here, I will let you do by AST. Okay, this one will be, you use AST that we just studied. Okay, I'm gonna show the second one for you. Okay, so I'm gonna show this second one for you. So when you like to show this one, okay, so when you like to show this one, this guy turned out to be equal to what? This guy turned out to be series n equal to 1 to infinity of just log n over n. Okay, and you're gonna see that this term can be used, okay, this term can be used comparison test. We used to use comparison test before. I show you that log n, okay, you have n more than or equal to 2, okay, and you have log n more than or equal to log 2, and you have over n, okay, and you then have series n equal to 1 to infinity of log n over n greater than series n equal to 1 to infinity of log 2 over n. And for this one, it's going to be log 2 series n equal to 1 to infinity, 1 over n. And this one turned out to be divergent. Okay, so this guy is divergent. So you're gonna conclude that the series n equal to 1 to infinity of log n over n is divergent. Okay, and it's gonna turn out to be conditionally convergent. Okay, so I let you do the first one by using AST on your own. Okay, let me just prepare my space a little bit. Okay, so in order to conclude that the series is conditionally convergent, the thing that you need to show is going to be the series itself is convergent and the absolute value of the series turned out to be divergent. The last question, okay, the last question gonna be, you like to determine whether the series is absolutely convergent or conditionally convergent. The step for doing this one gonna be, so it's gonna be two steps. Step one, you must show, okay, so you must show the series n equal to 1 to infinity of absolute an, okay, so it's gonna be convergent or divergent. If it turn out to be, okay, so I'm gonna say not show, show is gonna be you know the answer. Let's just check. So you check whether this guy convergent or divergent. If the series of absolute value of an is convergent, then you just say, okay, so it is absolutely convergent. Okay, so it's gonna turn out to be absolutely convergent in this case. If the series of absolute an is divergent, okay, then go to step 2. Okay, so you go to step 2. Step 2, for step 2, okay, so for step 2, you're gonna check the series n equal to 1 to infinity of an, okay, for conversion or diversion, okay. If the series an n equal to 1 to infinity is conversion, then it is conditionally convergent. Okay, and if the series n equal to 1 to infinity of an is divergent, so it is divergent. Okay, so for this question, it's going to be 3 options: absolute conversion, conditionally conversion, or divergent. Okay, so it's going to turn out to be 3 options. And the way to do is going to consist of 2 steps, step 1 and step 2. Okay, so it's going to consist of 2 steps in order to reach this conclusion. Okay, so we're gonna do step 1. Okay, so for step 1, you just have series n equal to 1 to infinity of absolute negative 1 to the n square over n to the third plus 4. So this guy will be series n equal to 1 to infinity of n square over n to the third plus 4. And here is turned out to be a good candidate to use. Okay, so you use Bn. Okay, so you use limit comparison. Okay, so this one will be your sequence, right? So you like to compute limit n go to infinity of the green sequence n square n cube plus 4. Okay, and you see here that you like to adjust the power here 2 and 3. So you use the trick that we did last clip. So you have n square n down here, and this make, okay, so this make limit n go to infinity, and you have n to the third over n cubed plus 4, and this limit is equal to 1, not equal to 0. Not, I'm gonna say more than 0. Okay, so you see that this one is called limit comparison test. Okay, so this one is called limit comparison test. And the way to use this test will be you must test series 1 over n is divergent. So, okay, you can conclude that your series n equal to 1 to infinity of the green guy. So it's gonna be divergent as well. So you have the series n equal to 1 to infinity n square n cube plus 4 is divergent. Okay, so this one will be your step 1. So it's turned out to be divergent. Okay, so it's turned out to be divergent. So you go to step 2. Okay, so we proceed to step 2. So we proceed to step 2. So we consider the series n equal to 1 to infinity of negative 1 to the n square over n cubed plus 4. Okay, and you see that this one is a good candidate for using alternating series test. So use AST. Okay, so number 1, you just check limit n go to infinity of n square over n cubed plus 4. Okay, and we learned that this guy turned out to be equal to 0. Okay, so this guy turned out to be equal to 0. And step 2, you need to show decreasing. So you need fx, okay? So it's going to be decreasing. So you need fx equal to x squared, x cubed plus 4, x greater than or equal to 1 is decreasing, okay? So you need to differentiate, okay? And you need to conclude that this guy turned out to be decreasing. So I'm gonna let you do this one on your own first, and then I give you the solution during the recitation, okay? So you must have to show this one, and it's gonna turn out to be conversion by AST, okay? And it's gonna turn out to be conditionally conversion. Okay, so for this one, we can answer conditionally conversion, but please finish this one on your own first to see whether you understand what am I doing. Okay, so that is gonna be everything that I like to cover in this clip. Okay, you're gonna have another one. It's gonna be easier than this one on the it's gonna be easier to understand. However, the calculation that you're gonna see in the next clip is gonna turn out to be serious for limit. Okay, so let me prepare myself some space when I explain this one. Okay, so that will be everything for this one. What have we learned? We learned alternating series. It's called AST to test conversion. It's called test for diversion for limit n go to infinity of bn not equal to 0. And another thing that we also study is going to be about 3 words. It's going to be absolute conversion, absolutely conversion, conditionally conversion, or diversion. Okay, so that's all.